So this is the second workshop for XFLR5. I'm gonna cover stability analysis and VLM2 analysis in detail. And I also might get into how to design an elliptical wing, but that really depends on which time we have. And I don't want this to be super long. The last video was like um 1 hour and 17 minutes. Um, we'll see. We'll see how long this goes. But yeah, it is currently 9:30 p.m. I have homework, and yeah, so I'll just see how quickly I can do this. But yeah, of course, if I do it quickly, that doesn't mean I want to like easily mess stuff up. But yeah, share my screen. So I hope y'all see what I'm seeing. This is the teams, and this is XFLR5. So I already did do an analysis on a plane that I quickly designed. Well, not the whole plane, but the wing and the empennage. Um, so before you do any of like a stability analysis, one here, or any analysis in general, first you need to go back to your X-foil direct analysis, right? And I covered all of this in the first video. So if you're confused or have any doubts, you can go back to that one. So before you want to do any advanced analyses, I guess you could call them, you need to do batch analyses on particular airfoils, like whatever airfoils that you choose. How do you do that? Analysis, batch analysis, and um you do need these very exact Reynolds numbers, right? Like the speed, the I think, and critical. I think that means like environmental conditions. Like it describes environmental conditions. These two can change, to whatever you want, but these Reynolds numbers, these have to be the exact ones that I have, right? Like from the first one all the way to the 44th one, it has to be these numbers, or to my knowledge, the analyses do not work. And um, in the description of the video, I will try to have like a photo, or like maybe just type it out, all the Reynolds numbers, so that you'll have easy access to them. Oh God, what did I do? Oh, I don't know. What was this before I do something stupid? So yeah, you need all to do all that. Let me go back to that, and then you have all this data. Um, alpha. I like to do minimum -20, maximum 45, an increment of 0.1. Um, yeah, threads is like how much power your computer uses to do the analyses. And then you click analyze, it does all that for you, and you get all these squiggly lines. I also did explain what each one of these graphs mean. Hopefully I did in the previous video. Um, I'll go over them again in the future sometime, but for now I want to focus on the more advanced analyses. Well, advanced isn't like, okay, yeah, they're fairly advanced, but whatever. Design or and playing. Okay, so before the second thing you need to do before you do anything is you go here, you click define plane. I already did that, and then once you do that, current plane, um, edit. You go to, well, the first thing you do, I'd recommend is defining your weights, right? And so how do you do that? Once you open, you click define plane, edit plane, all those like multiple of those options in that drop down open to the same thing, right? And then you click plane inertia, and then you click main wing. This is you defining the weight of the wing, right? And all these numbers, the coordinates of the CG, um, the inertia in the center of gravity, all of these, it defines them for you based on the dimensions you get, right? And then you say you define wing mass. Actually, me let me verify what I'm telling you was correct because I don't want to lie to you. Plane, define plane. Okay, yeah. So it does let you define the weight, the masses of your wing, your empennage before you define any of the dimensions, right? Because what I was confused on was maybe it wouldn't let you define your weights before you define your dimensions, but that's not the case. So yeah, we're good. So another way is clicking on a name. Yeah, right click and then click edit and get back to this window. Plane inertia. I basically chose these from the top of my head. A 1 kilogram wing for an RC plane. Well, the weight really depends on how big it is, but you know, yeah. Elevator. Elevator is horizontal stabilizer 0.5 and 0.2. And say you define your weights before, like, after you want to define your weights after you do analyses, right? It will literally say that all your analyses are invalid and it has to delete all that data because you didn't add weight data, right? So it's very important to define your plane inertia. And so after you do that, you can move on to defining the dimensions. So click define. Here I have, so one of these, the second row under the column of y parentheses or length, wingspan, you have to like define half of your wingspan, right? So I put 12 here, but the total wingspan is actually 24, right? So this is how it works for the main one. And then chord, I've said 8-inch chord. Offset, I'll show you what offset is. Yeah, so it adds like this best thing I could say is sweep, but we're not testing that necessarily. Maybe in the future I'll test all that. And then dihedral is like, you're flat and then you angle it up, flat, angle it up. Um, that's to show you all. Funny. Yeah. Hopefully. Okay. Yeah, let's try it. Let's for not 20, 5 maybe. Okay, apparently it's acting weird, but moving on. Wait, don't worry about that later. Sometime. Twist literally twists your airfoil, right? There's some cases where this might be useful, but honestly, I've never had to do something this crazy before, crazy advanced, whatever you want to call it before. So yeah, and then I think one of the best features is that it lets you define the top and the bottom of your wing shape, right? So you could use airfoil, you could use like one airfoil for the top, right? And then one airfoil for the bottom. What this allows is like more like dynamic testing, right? Because you're not stuck with just having to stick with one particular shape. You can sort of experiment, see what works for your case. Um, I've never really, for the competition that I do this for, I've never really had to do something this advanced, but if you're into this, if you want to look into it, then go ahead. Um, Next thing would be defining elevator or the horizontal stabilizer, right? And in this case, I put 5 inches. It gives a 10-inch wingspan because this is only half or it is 5 inches. But well, I didn't really like you'll see what chord actually is, so I'll change this to 9, right? And then change this to 9, right? It's the width of it's the width of the particular lifting surface. Lifting surface being the the general definition for wings and empennage. And just a 5, and just a 5. Offset, dihedral, we already tried messing with that twice. We already looked at that. Um, Foil, yeah. So from what I've seen, there's certain airfoils that work better for empennage and certain airfoils that work better for wing. Um, this becomes more obvious to you the more you get used to it. Um, it is like you will have to do research. So yeah. Typically, how we determine that is we find a list of airfoils that we think would suit empennage and wing, like two separate lists usually, and then which we get from like previous reports, proposals, research, as I said, and then from there we do analyses, testing, and all that, see which particular shape would actually give us a desired advantage. And then finally, the vertical stabilizer, right? This one's a bit iffy, weird, right? I put 4, it gives you 8. It's actually 4 inches. So, um, although I might be stupid, I think I went over this the previous video. Might have gotten it wrong. We can honestly, I'll eyeball it and see if I feel like it's 4 inches. Okay, does not look like 4 inches. That is in fact 8 inches. My bad. So yeah, same thing here. 5 inches, 5 inches for core. Airfoil, the same thing. They they um see it thinks I changed something. I really didn't. So X that should solve it. And then yeah. And then just for y'all, I will delete all the data I have to redo. So if you want to delete the data of a particular analysis, just click on it. Well, right click on it and then delete associated all operation points, op points, or your ops, apparently. And save. Always remember to save. Save pretty often, honestly, because then it crashes if you don't. And then, yeah, this is it, I will do my very best to explain this in simple terms. So this is, to what I remember, a side slip analysis. A type 5 polar is a side slip analysis. What this helps you do is determine the maximum angle of attack or lifting surfaces can bear when the plane when they're in a turn, right? So when they're turning, what is the maximum stall they will have, right? That is the best I can give, given the cruise condition. That is the best way I can explain it. And then you want all of the rest of this to say the exact same. So type bipolar, when you click define analysis and say you want to do a side slip, right? Okay, wait, wrong one. Okay, analysis. Um, okay, define an analysis, yeah. And then, yeah, you want to make sure it's selected type 5 if a side slip analysis is what you want to do. And then you go to analysis, it should be ring vortex and viscous inertia, use plane inertia, reference dimension, wing plane form. Um, and then aero data. These two are constants, right? They're yeah. And you can look at them in imperial units or international units. Extra drag. This is pretty interesting. So say you're building a banner plane, right? A banner towing bush plane, right? Which is the design, build, and fly competition this year. Um, this is how you would add the associated data to that. And then um, I'm still looking into it. In a future video, I'll probably cover what this means. I also don't know how accurate it is, but yeah, it's there. Go back to polar type. Make sure you have your desired um, cruise condition, and then alpha is like the initial angle of attack, right? So imagine a plane, right? We have your landing gear, and then due to you having a landing gear, there is a tilt, right? That is that is the overall plane tilt, right? And then when you mount the wings onto the fuselage itself, right, they'll usually have like their own little angle, right? So this particular one is the angle of the wing itself when it is mounted, right? Which should be close to zero. Sometimes people do like, you know, 2, 3 degrees up or down. Um, but yeah, if you're just doing a basic analysis, um, zero should be enough. And then 44 miles per hour save. And then I already have one. So I'm gonna click discard. Y'all can click OK, but I will click discard. Y'all click OK, I click discard. Remember. And discard. Then before you do any analysis, make sure to click save. And then once you go over here, these two options, and I think that means initial LLT and sequence will both be deselected. I need y'all to make sure to select these two. And then you can define like your starting angle of attack and your ending angle of attack, right? Like basically it's like the initial condition and the final condition. And the analysis will keep going until it either reaches the final condition or it reaches a point where um stall becomes it stalls, right? The wing stalls. Yeah. And then increment is like, oh, how much are we going by in each analysis? So it goes 0.1, 0.2, 0.3, so on. Make sure this is also selected. It usually is all already selected, but yeah, just make sure it is. And then analysis, analyze, analysis, whatever. And yeah, okay. It'll keep going. So we have data for this. How do you read side slip data, right? So it started at our initial condition, 0. It kept going. 9.8 is your stall angle during a turn, right? Like the body cannot tilt more than 9.8 degrees during a turn, right? That's what it means. And given a margin of error, yeah, I'll say like 9 degrees conservatively and 10 degrees liberally, right? It really comes down to how well you design your plane, how well your plane is manufactured. Okay, wait, yeah. Okay. Next thing we're going to cover, stability analysis. This one is a wee bit more advanced, and honestly, like, um, XFLR5 is not the best option for the type of data that a stability analysis gives you. You probably want to try and do CFD. In the particular competition that I'm in, most teams do not do this, but the ones that do really good usually end up doing it, right? So it is a good goal to have in mind to figure out how to do CFD, right? And you can probably find better software for it, like um ANSYS, Autodesk CFD, SolidWorks, literally anything, right? However, it is a good way to get sample data, right? It's better than nothing, right? Not everyone can afford a fancy software. I will admit they're pretty expensive and hard to get. So it's best to have this than have nothing at all. So that being said, let's let's do it. And then yeah, I already defined it. So how do you define stability analysis? Stability analysis. Analysis, define stability analysis, analyze, make sure all of this is the same. Reference dimensions, you want to make sure it's wing plane form. Yeah, mass and inertia, we already defined that. Control parameters, you need to put at least one here. It will not work if you don't have one, right? You could try -1. I've actually never tried using -1. Yeah, crazy. You need to put 1. You can put 2, 3, 4, 5, 6. Literally anything but 0. And this one can stay the same. This one can put 0, be 0, unless you want to put something else. Arrow data, yeah, keep it the same. Unless you need to change it, and then extra drag, as I explained, right? Okay. Okay, I already have it defined, so save. Discard, save. Uh, select this, and then yeah, analyze. One thing to be discussed is the increment, right? 0.5. The best way I can explain it is the bigger your plane, the smaller you want this increment to be, right? Um, why? It's because how XFLR works is that the smaller you make the plane, the faster it will at the higher velocity it will use during the analysis, right? Which is something you don't always want. Like so, yeah. Um, our cruise condition was 44 miles per hour. If I put the increment at like 0.1 or whatever, it'll give me data starting at like 300 miles per hour, and I'll never reach a particular data point that says that has the cruise condition that I want, that is close to the cruise condition that I want, right? So make sure to have it at least 0.5 for like the given dimensions of this plane, right? You can have an initial condition at 0, ending at 20. Really, these are angles of attack, but you can call it initial condition, final condition, initial angle of attack, final angle of attack, whatever works, honestly. Make sure, again, these three are selected, and finally, analyze. Also, something very important, make sure your computer's plugged in, because these analyses do take up a lot of power, a lot of juice. Uh, So what this is showing us is um the plane going through different angles of attack, right? Until it reaches natural stability, right? And how do you know that your cruise condition is good, right? Is that um you have an angle of attack that is close to 0, and then you have, and it actually gives you data that's like, you know, around your cruise condition, and then a CLCD of like um the closer to 1 the better is the best way to say it. And then coefficient of drag is like um when you put it in a ratio with coefficient of lift, it's like coefficient of lift is supposed to be like as high, well, not as high as it possibly can, but it's supposed to be like this difference that is like advantageous to where you're not particularly worried that the drag would pull you back necessarily. I'll explain this in more detail later. Yeah, but yeah, I'll have like a terminology video probably in the future where I can explain these things better, and also these stuff as well. These things, well, yeah, some of these are pretty obvious, but yeah. And then at 18 degrees at angle of attack, it's saying that you will be at your ideal cruise condition. Your angle of attack of the overall plane, right? Not just the, actually, let me correct myself there. 2 years. 2 years. Hey, you know what? I forgot. Okay. Forward one. Forward. Oh, okay. So what alpha is the, say, imagine, well, okay. So you have an imaginary line going through the center of your wing's airfoil, right? Um, it is It is the angle of attack, which is like the difference between. Wait, okay, I opened Discord. Great. Now my reputation is forever ruined. Um, it is, anyways, the is the angle between how the air is flowing and the imaginary line, right? So it's like sort of a triangle. This line, and then the airflow is this line. It's going this way, and the chord is going this way. That is your alpha here. And this is your actual, like, okay, the entire plane, both lifting surfaces are going to 18 degrees, right? Alpha is just in reference to the chord line itself, right? Or like, I'd say the center of the wing itself is the best way. I hope that was a good explanation. I'll probably explain these better in a later video. But yeah, that is how you do a stability analysis. Um, what other data does this give you? CLCD, the ratio of your lift and your deck, your lift to your drag. You probably want this to be pretty high if you want your plane to actually fly. It really depends on what particular plane you're having, flying object you have, right? RC planes typically have like 12 to 16, but given the dimensions of this particular plane, it's more like a UAV. So it can be lower and still be a good ratio. That is arguably the most important thing to get from this. Again, a CFD software is probably more accurate than this. However, this is better than nothing. So, you know, good, good stuff. I hope it wasn't boring. Uh, do I want to cover elliptical? No. Okay, so I will cover elliptical wing and more terminology in a future video. For now, I think I want to finish. So stop sharing my screen. Uh, in a past, well, based on the one other video that I have, the mic quality was terrible. I hope it's better this time around, and um, yeah, the lighting's kind of weird too. Yeah, I'm obviously not the most experienced YouTuber, and I'm a college student and an employed person first. So yeah, um, please like and subscribe. Feel free to post any questions in the comments. I'll try to answer them as soon as I can. But for now, this is the end. See you later.